So we discussed about some aspects of defects in solids. So we'll continue with that and then move on to diffusion in solids, and then question about why, thin films. Okay. What we saw in the last class was in a periodic perfect crystal lattice, well, there are no perfect crystals. Crystals always have crystal defects. So vacancies, missing atoms, which are called Schottky defects, and atoms displaced to non-lattice positions. These are Frankel defects. And the other form of defects are the induced one. So you put those defects inside the solid. These defects are called dopants. So we intentionally replace the atoms in a crystal by foreign elements or atoms. So these elements replacing the lattice atoms could be smaller or bigger. And I mentioned that when that happens, so there's a lattice expansion because you have a larger atom replacing the lattice atom, which is smaller, comparison of sizes there, and a smaller atom replacing the lattice atom. So there'll be expansion and contraction of the lattice at those points. And so X-ray diffraction statistically gives you information about what is the overall decrease in the lattice parameters and the overall decrease or increase in the lattice volume. We also have these Frankel pairs, a combination of interstitial and the vacancy. You can also have a combination of a replaced atom. If this atom is replaced by a bigger or a smaller atom or ion, so you can have a pair between that dopant ion and the vacancy. Right? I also mentioned that such dopant vacancy pairs are required for making qubits in when you're dealing with a diamond lattice. Some fascinating things. So today I'll also tell you about why crystals become colored. But before that, a few more aspects of defects in solids. Again, if you see the open circles and the dark circles there, these are the lattice positions, alternating two different kinds of atoms occupying the lattice sites. So all this is possible. For example, what you see here is, the circle here, dark circle here is gallium, arsenic. The smaller one is boron, this one. And the bigger light circle is indium. So you can have these possibilities also. This is what is meant by doping, okay? So you can basically have a gallium vacancy, a Schottky defect, a vacancy created because you have a missing arsenic atom, and arsenic going to the interstitial site. This is basically a gallium arsenide lattice, gallium arsenide, the well-known semiconductor. And you see, you can also have this missed site occupation. Okay, This can also happen. Gallium at arsenic site and vice versa is also possible. Now, we can replace the atomic positions, lattice positions, by indium. We can also replace the lattice position by boron. No? So this is a classic example of how in a gallium arsenide lattice, you can bring in additional foreign elements in the form of boron or indium separately. This we do, as you know, in semiconductors. A perfect semiconducting crystal is not so conducting, whether you take gallium arsenide or silicon. I've also shown you this table where you're seeing this interesting change in the resistivity of silicon or gallium arsenide before and after doping. So 3 to 5 atom percent of dopants brought into the crystal lattice can change the resistivity values by 2 to 3 to 4 orders of magnitude. That is a beauty of doping in crystals, doping in lattices, doping in compounds. So in some cases, doping brings about changes in electrical properties. In some cases, you see changes in magnetic properties. In some cases, you see changes in optical properties. So doping can be responsible for various changes in physical properties. Okay. Yeah, these are all different types of all the way from missing atoms in the lattice to lattice atoms replaced by foreign elements. Okay. So you also call that, this is called also the impurity doping, because these are basically impurities. When I'm bringing in a pure gallium arsenide, when I'm bringing indium, so I'm actually, what am I doing? I'm replacing, you see, that side, the gallium side with indium, right? So I'm creating a little bit of impurity in the lattice. To what extent indium can replace gallium, whether it is 3 atom percent or 7 or just 1, that is called the solid solubility. So thermodynamics determines that. How much of a foreign element, which is larger or smaller in size compared to the lattice atom size, can replace a given lattice position. Okay. I talked about the Frankel pairs already. Now coming back to the one important concept of coloration in crystals. So it all started more than a century back with the explanation or invention or discovery of what are called color centers. Crystals get colored because of impurities. So you can intentionally create these impurities in crystals. And one example is here. I have NaCl lattice, Na plus, Cl minus, a periodic lattice of, the sodium and chlorine ions, sitting next to each other, forming a face-centered cubic lattice. And a few defects, here is an example of missing ion there, right? What is missing there? You have the positive sodium ion, negative chlorine, again sodium, and an anion is missing there. And when that happens, you have a trapped electron there. And these trapped electrons give rise to a coloration of the crystal. So an F center, Faber, F stands for Faber in German, which means color. An F center stands for color center. It's a type of a crystallographic defect in which anion vacancy in a crystal is filled by one or more electrons, So you have an anion vacancy, so it has a potential to attract an electron. So an electron gets trapped in that vacancy. You can also create cation vacancies. So you have 5-6 different types of color centers, but F center vacancy was the first one to have been discovered. So if you take any solid state physics book, solid state physics by Decker, solid state physics by Charles Kittel, all these systems would have covered the topics on color centers. Okay. Now, depending on the charge of the missing ion in the crystal, or mainly due to the reason that when a compound is, say, heated to high temperature, we're talking about metallic oxides, so the electrons get excited and get displaced from their respective positions in the crystal lattice. But while doing so, these electrons leave behind some electrons in the vacated or vacant crystallographic places. Okay. So this leads to the phenomenon of coloring of compounds. That's why these color centers make crystals colored. So if you start with zinc oxide, if I take zinc oxide, it's a wide band gap semiconducting material, a band gap of about 3.4 electron volts, and so basically these wide band gap semiconductors are transparent to visible light. Now they have plenty of applications, especially in thin film form. Most of these display devices, touchscreen devices, use these wide band gap transparent conducting oxides, because for certain applications, you need a top electrode which is transparent and also conducting. See, imagine you have a solar panel and or a light emitting diode. So you need to give contacts. So you have bottom electrode and a top electrode. And the top electrode cannot be a metallic electrode, right? Because the light that is emitted in the process should be transmitted through the top layer. So the top layer should be both transparent and also conducting. That's what is meant by transparent conducting oxides. So this is what it is. You start with zinc oxide, which is a ceramic, which is typically obtained in a powder form. You see that white flowing powder is what zinc oxide is. I can convert it into a single crystal, when you convert zinc oxide crystal, it should be a nicely white-looking crystal, right? So this is a crystal obtained from the powder of zinc oxide using some of the standard crystal growth methods. But the issue is, so it looks a little colored. That means it must be having certain amount of defects incorporated during the growth process, right? So yellow color comes in when you have lead and cadmium impurities. Gray color when it contains zinc metal, excess zinc metal, or some minerals, defects or incorporations in the form of minerals. So these are synthetic zinc oxide crystals that are prepared in the lab. Red and green colors are associated with different concentrations of oxygen vacancies. So zinc oxide, alternating zinc and oxygen atoms in the lattice, and then oxygen vacancies or zinc vacancies can bring about coloration. And this is a classic example of how oxygen vacancies can make the crystal colored. So color centers, in other words, are also, so you're trapping charge carriers in these color centers, right? And this charge carriers excitation leads to emission in the wavelength, in the visible range. And once the emission happens in the visible range, to the naked eye, we see a different color of the same compound from its, pure form. Yeah. You know about silicon. So again, going back to the basic concept of doping, if you have a perfect crystalline lattice of silicon where you have alternating silicon atoms, right? And, each silicon atom is covalently bonded with 4 neighboring silicon atoms, right? And when I bring in phosphorus, which is a pentavalent element, it can share 4 of its electrons with 4 neighboring silicon atoms, like the complete shell of silicon, what silicon does with 4 neighboring silicon atoms. See, you can also understand now in a perfect silicon lattice, there are no excess electrons. All these electrons are shared with the neighboring silicon atoms. But the moment you bring in phosphorus, the important thing about doping is the following. The foreign element that you bring in, you want it to replace the lattice atom. When these foreign atoms sit at interstitial position, they may not participate in the bonding process, so they may not contribute to changes in the, say, for example, electrical properties. The way you see changes in electrical properties happen, you may not see that happening when the atom replaces, when atom goes into the interstitial side. So these are called substitutional impurities. You want the foreign atom to be a substitutional impurity. The name itself suggests that you want this foreign atom to replace the existing atom and substitute it, right? You replace silicon by phosphorus or boron. So what happens when a silicon is replaced by phosphorus? It brings in 5 electrons. 4 electrons participate in the bonding with 4 neighboring silicon atoms. But mind you, the ionic sizes of silicon and phosphorus are not the same. So there will be local distortions in the lattice wherever phosphorus replaces silicon. So, and in this process, since it's a pentavalent element, you have an additional electron that is sort of free to move in the lattice. That's how when you measure the mobile electron density before doping, before bringing in phosphorus, okay, and after doping, you see a significant increase in the carrier density. This is called the carrier density. While we know that metals have a sea of electrons, they have Fermi sea. Electrons are the charge carriers in metals, right? You don't talk about the presence of holes in metals. So the conductivity in metals is all from electrons, free electrons, so-called free electrons. But in the case of semiconductors, the conductivity can be, the total conductivity can be from 2 parts. Sigma electrons, in the case when electron incorporation happens in the lattice, or in the case of holes, right? So you can make a semiconductor into an electron-rich material or a hole-rich material. What is a hole-rich material? Instead of phosphorus, I bring in a trivalent ion. Boron is a trivalent ion. Indium, gallium, all these are trivalent ions. Now, when boron replaces silicon here, right, it only brings in 3 electrons. So it bonds with 3 neighboring silicon atoms. But then the lattice is depleted of one electron. So you effectively, you have a missing electron there that is hole, right? So in a semiconductor, you have mobilities coming from electrons as well as holes. Mobility is mobility from electrons, mobility of holes. Conductivity, total conductivity is conductivity from electrons and holes. So when you make it into an electron based semiconductor by phosphorus doping in silicon, so the majority of the carriers are electrons. You also have minority carriers as holes. Okay. So how do you know how effectively the electronic concentration is increasing in a, basically in a lattice like silicon lattice, from its pure form to the doped form? Of course, first you do a conductivity study. You see the conductivity versus temperature plot. You can easily make out when conductivity is measured for the doped one and the undoped one. So you can see which one is the doped one and which one is the undoped one. So for the doped one, the conductivity increases because you're bringing in additional carriers into the lattice. So the resistance or resistivity should decrease. So high resistivity for a pure sample and for a doped one, it decreases. This is the first test that, yes, the dopant inside the lattice is bringing about changes in the electrical property. Okay. That's why I also mentioned in the initial classes that it is absolutely important that you measure the property, resistivity. Of course, conductivity is just the inverse of resistivity, right? Resistivity in ohm meters, conductivity in Siemens per meter, right? Yes. So this clearly shows that there is a significant change in conductivity, but what is the extent of additional carriers that you're bringing into the lattice? Okay, can only be determined by experiments like Hall effect. And Hall measurements, Hall effect measurements, will also give you information about the type of the charge carriers. Whether you're dealing with electrons as majority charge carriers or holes as majority charge carriers. That's the power of Hall effect measurement, which is a very important tool. And thin films are essentially very much preferred for Hall measurements because of, well, when I teach about Hall measurements, Hall effect measurements, how you get carrier density, Hall coefficients, etc., you'll realize that the Hall voltage, the measurement of Hall voltage will be much better when you deal with a thinner sample. Even if you're doing Hall measurements on a bulk sample, one would like to reduce the thickness of the bulk sample. So if you're doing the same measurement on a thin film sample, naturally the thickness will be very small. You're dealing with a few hundred nanometers of thickness of the sample for Hall measurements. That's why Hall measurements on thin films are always viable. Okay, that's what is about doping in a semiconducting lattice like silicon. You see changes in electrical resistivity, which means changes in electrical conductivity, and these changes bring about extraordinary changes in electron mobilities, carrier densities, and so on. So this is an example of what doping can do in a semiconducting lattice like silicon in terms of changes in electrical properties. We also know that, unless you have a P-type semiconductor and an N-type semiconductor, we have a P and N-type semiconductors made of silicon, say, then you make a PN junction, and then that's called a diode. And then you talk about photovoltaics, solar cells, conversion of light energy from the sun to useful electrical energy. See, all that happens because of doping leading to PN junction formation and so on. Now I'll give you another very interesting example of doping. This is also doping that brings about changes in optical properties. You see this? Now, we looked at a silicon lattice. Silicon has a band gap of 1.1 electron volts. And with doping, with phosphorus doping, you're getting a donor level very close to the conduction band. So donor level sits a few milli electron volts below the conduction band. So, even at room temperature or a little above room temperature, it's easy for these carriers to be pumped into the conduction band and conduction happens. Okay. For electrical conduction to happen, you should either have a completely filled band, completely empty band into which you can push carriers to move around, or you need to have partially filled bands, half filled or partially filled bands. A fully filled band will never give you conductivity. A fully filled valence band separated by a completely empty conduction band with this forbidden gap, no, you will not get conduction. That's why doping helps. Or you should be able to give sufficient energy for electrons to move from the valence to conduction bands, which is possible in low band gap semiconductors. But you take example of, say, alumina. Alumina is a naturally occurring compound, which you can get in many places around the earth, right? So this is the raw form of alumina, and a little processed form of alumina is white in color. See, most of these ceramics that are white in color, that means they also have higher band gaps, okay? A compound which is blackish in color, you can expect it to be conducting, but not a white compound like this. Zinc oxide also. The moment you see this, you should realize that it must be an insulator or material with a wide band gap, anywhere about 3 electron volts. Well, the normal semiconductor band gap range, silicon, gallium arsenide, and other 2,6 and mostly 3,5 compound semiconductors, the band gap ranges from 0.7 electron volts for germanium to all the way from 2.5 electron volts. But when do you start calling insulators or insulators? Well, anything above 4 electron volts is an insulator. But 3 electron volts also, if you have a material with a band gap of 3 electron volts, it's not easy to pump charge carriers from valence to filled valence to empty conduction band. Enormous energy you have to give to the lattice for the electrons to make a transition. But you have a class of materials, wide band gap materials, where extraordinary things happen when these systems are doped. And this is a classic example. So alumina is an insulator to start with. It has a band gap more than 4 electron volts. So it is an insulator. Now, what is alumina used for? It's a high melting point compound. So, in the last few classes last week, you're seeing how to make materials, right? If you want to make barium titanate, I start with barium carbonate, titanium dioxide, mix them in stoichiometric proportions, right? In the powder form. And the mixtures have to be heated in a furnace. You also have seen how to generate high temperatures, is it not? Different kinds of heating elements, nichrome, canthal, silicon carbide, supercanthal, that is molybdenum disilicide. All these heating elements can provide heating at different ranges of temperatures. Suppose you have to make a compound at 1500 degrees centigrade. right? So if the individual constituents are mixed up, of course, but then you have to heat up the mixture to 1500 degrees centigrade. You need to have a container in which the heating has to happen. That is one. Second, you don't want any impurities from the container compound, the basic constituent of the container, to contaminate the compound that you want to grow. Suppose you want to mix A and B to get C. You don't want an additional D coming from the so-called container material. So that means the container material should have a higher melting point than the melting points of the constituent compounds. But any compound, you see, if the melting point is 2000 degrees centigrade, and if you heat the material to say 1800 degrees centigrade, 1700 degrees centigrade, there will always be energy given to the surface atoms, and surface atoms can start diffusing, right? So you can start seeing contamination. So because of by virtue of its high melting point, alumina can be used as a crucible material. So as you see that it's a nice crucible material, and if you have to do heating of compounds in a furnace, the first thing that comes to our mind is alumina crucible. And these crucibles are available in different forms, in the form of these crucibles of different sizes, these rods. So that's a basic use of alumina. The well-known ceramic material used for making highly dense crucible materials, dense crucibles that are used for heating compounds. Now, similar to what we have seen in the previous discussion, doping silicon with phosphorus, bringing in additional electrons. Let's see what happens if a part of aluminum is replaced by, say, chromium. I mean, this work was done more than 50 years back. The moment you bring in chromium, about 3 atom% of chromium into alumina, you see, the color of alumina changes from white flowing powder to this nice looking brick red color, maroon color. And so chromium doping visibly is giving you a color change of the material. Okay, so doping normally can be represented in this way: Cr3 plus, double dot, colon, Al2O3, or it can be Al2O3 double dot Cr3 plus, which means Cr3 plus is an ion that has replaced one of the lattice atoms or lattice ions. In this case, of course, chromium can replace aluminum because it can replace, it's a cation, it can replace another cation, which also has a 3 plus valence state. Now, what is the use of now this? So you have a ceramic in the form of pure alumina. Aluminum oxide is also called alumina, Al2O3, which has quite a number of applications as crucible materials, right? Which is, of course, a very important application. Now, what do you do with this? Traditionally, all these colored objects, coloration, now you can make pigments and paints using this doped alumina powder. Obviously you can see that. Nail polish and the maroon color that you see on ceramic pottery, because it's a non-toxic compound, so it's no problem. So you can make paints and all kinds of things. So that's the second application of alumina with chromium doping. So the color change. In the previous case, we shown changes in electrical resistivity. Here you see changes in the basic coloration. You see just about 3 atom% of aluminum completely changing the color of alumina to that beautiful looking maroon. Is that all or anything else? Yes, there's more to this. Now I can take this alumina powder, subject it to a crystal growth process. That means I take this alumina powder, melt it, take it to its melting point. I can use one of the crystal growth methods, Bridgman technique or Chakralovsky, the various crystal growth methods, and I make a crystal out of it. So this is chromium doped alumina. And then if I shape this raw crystal that is grown using one of the crystal growth methods, and you get this beautiful gemstone, right? It is faceted and polished nicely. You see that? What evolves out of, so you started with alumina, you doped it with chromium, and chromium creates, brings in this maroon color into alumina. And then you make a crystal out of it. Of course, you can also make a crystal out of alumina, which will be a completely a white colored crystal. And this crystal is one of the most precious gemstones. This is nothing but the ruby. The ruby we talk about is nothing but chromium doped alumina. It can be easily grown into crystal form at the lab level. Now, does it end there? No. You take the ruby crystal in the form of a rod, and you have a flash lamp arrangement around it, and more than 50 years back, when this ruby crystal was used, stimulated emission was seen, leading to lasing action. So the first solid state laser ever discovered was the ruby laser, right? So what you do here is, you create this, you have this forbidden gap, no? In this wide band gap semiconductors insulators, where the valence and conduction bands are separated by 3 or 4 or more electron volts. But these dopants create these special levels. These are called the mid-band gap levels, and that is where when the light is pumped in, these transitions happen non-radiatively, and then the lasing action happens due to population inversion, which is triggered by, again, another light pulse, photon pulse, leading to a wonderful emission of radiation at a specific wavelength. So in the case of chromium doped alumina, which is named as ruby, the lasing action happens at 694.3 nanometers. That's the first red light emitting laser that was ever discovered. So it was done more than 50 years back. This is amazing. Now, where have we gone? So today we have my senior colleague the other day, he got his cataract done. He said it was just done in 10 minutes, using laseroscopy. So lasers are used in various levels of eye treatment. So in a very useful way, lasers can be used in eye treatment of eyes. The powerful lasers can be used as a cutting source. Lasers can also be used, very high power lasers, extremely high power lasers, can be used in creating thin films from solid materials. You'll see that when you learn about the thin film growth process. You see the beauty of this, but just single slide. You start with the alumina raw material. You process it. You get that a nice white flowing powder. Dope a little bit of chromium into alumina. It changes its color. So see, in silicon with phosphorus doping, you're bringing those additional electrons into the lattice, and the conductivity of the silicon lattice changes. Here, it's not about conductivity. It's about changes in optical properties, right? So two separate examples, but both have these drastic changes happening because of doping, In one case, you see the changes in electrical conduction. In the other case, this case, changes in the optical properties. So chromium doping, you see the coloration change, the basic applications of alumina, that's how it started. And then, people always know that, you can make crystals, especially these wide band gap materials, where normally visible, transparent to visible range. You'd like to make crystals out of it. Of course, coloration can happen because of doping. Okay, so if you make a crystal of alumina, say crystals of alumina also play a very important role. There are different types. Alpha alumina, one crystallographic form of alumina is called sapphire. Sapphire has lots of applications. A crystal of sapphire is also very expensive. It has lots of applications. For many thin film growth applications, this crystal sapphire, which is alpha alumina, is used for thin film growth. So sapphire is used as a base material. Especially sapphire is a very good material for many microwave applications. See, how many applications you're seeing from an insulator, right? So whether you deal with metals, alloys, semiconductors, insulators, each one has its own form of exciting applications. Yes. So crystal, you polish it, you make it a valuable gemstone. And of course, the other form of that crystal, this is a crystal of the same material in the form of a rod. And then there's a flash lamp around it. This is a basic arrangement to build a solid state laser. Laser is light emission by stimulated, light amplification by stimulated emission of radiation. That light amplification, stimulated emission, all that is a part of, that's why you need a flash lamp here. And you generate a laser, and this laser has plenty of applications today. Right? See how amazing it is. Two sets of examples. One, the microelectronic industry wouldn't have existed without our ability to dope silicon with elements like phosphorus and boron, right? Go to make PN junctions, diodes, photovoltaics, conversion of electrical, visible light, visible photons into usable electrical energy. But here is a case where you transform the material into a colored one, make a crystal out of it, and then that crystal can be used as a laser material. Yeah. Okay. Good. So if you have a wide band gap system, and what you see here on the left top is, this is actually a thin film of zinc oxide, right? Zinc oxide again is one of the most prominently used wide band gap materials with a plethora of applications. It's a transparent conducting oxide. Transparency and conduction are both required, as I told you, in some applications. If I want to have a top electrode, if the device is emitting light, and if this light emission, of course, the light has to come out of the device. You can't afford to have a normal conducting layer as a contact electrode, right? Light cannot escape through that. So you need to have a material that is transparent as well as conducting. So that's where a class of materials, these wide band gap materials, indium tin oxide, one of the well-known TCO, transparent conducting oxide materials, but indium is expensive. So there are alternatives. So zinc oxide, aluminum doped zinc oxide, we can make it into a transparent conducting oxide. It has many applications. So what you see here is a thin film of zinc oxide grown on a substrate, just a glass substrate. But just to show the transparency, this small piece of substrate, glass substrate on which zinc oxide is grown, is kept on the printed letters zinc oxide. So we have printed zinc oxide on a paper, and you keep this. So if I keep a glass slide, obviously you see the letters beneath the glass slide, right? But on the glass slide, you also have a transparent conducting thin film. This interesting. Of course, you can only because it's the transparency is 95% and above. You just see through. Unless you put a multimeter on the top surface, you will not realize that it's a conducting film. So you have a glass slide, bare glass slide. You have a transparent conducting oxide. You put a multimeter here, multimeter there. Glass is non-conducting, and this is conducting. Okay. Now here, yeah. So that's what it is. You know, you have a fully filled valence band, say empty conduction band. This is a forbidden gap. In the case of zinc oxide, it is nearly 3.3 to 3.4 electron volts. So it's not easy to, I mean, you need to provide 3 electron volts of energy to pump carriers from valence to conduction band. That's a lot of energy. If you convert it into a thermal energy, so we want to provide it in the form of thermal energy, right? You'll be melting the compounds. You can excite those carriers using an external radiation. No, the system can absorb external radiation of sufficient energy, and that absorbed energy can pump carriers from the valence to conduction. But in such systems, so since the band gap is 3 electron volts, 3.5 electron volts, it's fall in the UV range, ultraviolet range. So the material, the band gap is transparent to the entire visible radiation. That's why these materials become transparent. Okay, but these wide band gap systems can be, tuned in terms of their color, that like what you're seeing, and in some cases, the electrical property also changes. So one example we have seen is bringing about changes in electrical conduction with phosphorus doping in silicon. The next example is how the optical properties have been altered using chromium doping alumina. But in some cases like zinc oxide, you can bring in conductivity, changes in conductivity also, because zinc oxide, pure zinc oxide again is non-conducting. It's like an insulator. But then doping can bring about additional carriers into the lattice. At the same time, it becomes transparent. So that's why it becomes a transparent conducting material. Or since it's an oxide material, it's called a transparent conducting oxide material. It's very interesting. So this is a scenario. What you see is when there is no doping in the material. The moment you dope zinc oxide or any other wide band gap system, right, you start seeing the creation of these mid band gap levels. And what are all these markings? These markings are, from a simple photoluminescence experiment. So you excite the material with a sweeping band gap and record the spectrum on the other side, and you'll see the kind of transitions that are involved in the material. See, if you have a band-to-band transition from the valence to conduction band, so that transition should correspond to, so if, suppose you pump a carrier to the conduction band from the valence to conduction band, and two things can happen. If the electron is pumped from valence to conduction band, and if these electrons are itinerant in the conduction band, because that's an empty conduction band, right? And if this excitation of these carriers happen, if this excitation happens with the aid of photons, so let's say the lattice absorbs photons, and then it kicks electrons from the valence to conduction band, and if these electrons are mobile in the conduction band, I said For conduction to happen, you either should have you should have a partially filled band, half filled band or a partial filled band. This is an empty band into which you pump carriers. And if these carriers start itinerant, the itinerant in the conduction band, you see conductivity. That means you're measuring the resistance of this material and shine light of a certain wavelength, you see a slight decrease in resistance. And since that means increase in conductivity or conductance. Because you are increasing the conductance with the aid of photons, this conductivity is called photoconductivity. So there are materials that are good photoconductors. So light energy converted into electrical energy, photoconductivity, right? But in many cases, what happens, like in the previous example, when you pump carriers to the conduction band, right? So when an electron leaves the valence band and goes to the conduction band, it leaves behind a hole in the valence band, or it creates a level above the valence band. Now, the electron that goes to the conduction band, it normally forms a pair with the hole that is left behind. So that is, in semiconductors, we call it, it's an exciton pair, right? Exciton. So what happens in certain cases, the electron propagation in the conduction band doesn't happen, because for this electron, the upper level is the most unstable state. It doesn't want to stay there. It always wants to come back to its original state to minimize the system energy. So in doing so, if it comes and comes back or makes a transition back to the valence band and recombines with the hole that is left behind, right? Depending on the energy level from which the transition happens, you will see that much of energy. If this is E1 and E2, you have delta E. So delta E of emission happens. And if this delta E falls in the visible range, you see light emission. So you can see emission with the naked eye. That is called the process of luminescence. Exactly the light kind of light emission. In the previous case, in the case of ruby, it's a coherent emission, right? It's a lasing action. But in most of the solids, the light emission is called luminescence. So then luminescence is subdivided into two parts. You have fluorescence and phosphorescence. Fluorescence happens as long as the excitation source is on, right? The source is on, and this process of carriers going to the upper levels and making transition back, recombination leading to light emission is happening. Phosphorescence is, even after the source is cut off, right? You still see some emission happening because of detrapping of carriers from higher levels back to the lower energy states because of the existing thermal energy, say room temperature. So I'll continue with this tomorrow. Yes, see, this is, so you can see the thickness of the sample there. That's a glass substrate on which a very thin layer, it's about 60 to 70 nanometers of zinc oxide is coated, and that's a thin film. And you have the substrate there. It's a glass substrate. If you want to have a crystalline growth, you need to have a single crystalline substrate. This is just to demonstrate how nicely a transparent conducting layer can be deposited on glass substrate, and then the substrate with the thin film on is kept on zinc oxide letters printed on a paper, and you see that you don't even realize that there's a film on the top, right? So that means this 60 to 70 nanometers thin film of zinc oxide is completely transparent, as transparent as glass. Okay, yeah, this is what it is. It's called transparent conducting oxides. Okay, so I'll stop there.